What is up, you guys? Welcome back to the eCoreAcademy learning platform today. Please make sure to hit that subscribe button, hit that like button on this video, as well as hitting that bell to get notified on any of our latest posts. That's very much appreciated so you can keep our channel running, because both Anita and I really enjoy making this content for you guys. So without further ado, let's get right into today's lesson. Today's lesson is all about cones and cylinders, and it's all about discovering the properties of cylinders and cones. And this includes discovering the volume for each and every one of those figures, the cylinders and cones each, as well as their surface areas and their special principles and properties that are also alike. So let's get right into it. Volume of cylinders. So this subtopic is all about volume of cylinders. Cylinders are three-dimensional figures with oval or circular bases, and that's very important to know, and it's essential for cylinders because these are the basis of cylinders. This is what actually gives cylinders their 3D shape. So what happens is you have a circle for a right cylinder, which is a proper cylinder in which our volume equation will work for, and which will come across most of the time in geometry. So continuing what I said, circles are your bases in right cylinders as shown here, and what happens is every single point on that circle and infinite points, they extend out in segments all the way down for the given height, which is 12 centimeters in this case, until it reaches a stagnant line here, and also forms another circle in direct replication of this first circle, this base here, that's extended out into a 3D figure. And of course, your bases are going to be congruent shapes, congruent circles in this case. And let's get into the volume of cylinders, because that's essential to know for any 3D shape. So volume of a cylinder, just like any prism, is your base times your height. So the base of a cylinder is calculated by finding pi r squared. Now that equation might be very familiar to you guys, because it's just the basic area for a circle. So you're just finding the area of the base, or the area of the circle, that in this case for any right cylinder, and then what you're going to do is you're going to multiply that by the given height. So let's look at the diagram and plug in the values given into the volume equation. You guys are free to pause the video and try it on your own with the given equation that's here, and just come back, replay the video, and see if you got the right answer. So let's plug it in. So you have a radius of 7 centimeters, and that's representing the radius of the base. It doesn't matter which base you're using because they're both congruent in every measure. So if you have a radius of 7 centimeters, you're going to plug that into your base equation because you want to find the area of the circle, which is the base of the cylinder. So if you plug in 7 for r, your radius, you're actually going to square that radius to get 49, and then you're going to multiply it by pi. What you can do is you can use the approximation of pi, which is 3.14, or you can just use or you can just leave the answer in terms of pi, which is most accurate. So I'm going to leave the answer in terms of pi. So I'm going to square our radius, which is 7, but multiplying it by itself. 7 times 7 is 49, and then you're going to multiply 49 by pi, so I'm going to leave it at 49 pi. Next, what you're going to do is you're going to multiply it by your height, which is 12 centimeters here, which is indicated by h, and 12 times our base area of 49 pi is 588 pi. So that's the exact area of the cylinder. If not, you can substitute 3.14 and multiply that by 588. So let's move on to the next subtopic, and that is surface area of cylinders. So it's important to know two properties of three-dimensional figures. It's their surface area and their volumes. So let's look at the surface area of cylinders now. So the surface area, the equation for the surface area of a cylinder is 2 pi r h plus 2 pi r squared. So now if you look at the diagram, you can notice how the cylinder is sprawled out, and that's actually called a net. Whenever you take a three-dimensional figure and you basically unwind it, ravel it out into two-dimensional figures, you're actually showing the net of that three-dimensional figure. And each part of the equation represents the different shapes in the net, and that's actually also very important to know. So as you can see here, you can see this 2 pi r h. This first part of the equation is going to represent our bases, because if you think about it, there's two circles on the top and the bottom. So these two circles, these are your bases. And however, when you ravel out the center of a cylinder, when you ravel it out, it's actually going to become a rectangle. And that's important to know because with the properties that are given in your volume equation, you can actually use that to find the surface area. So surface area is basically the total area of the surface of a three-dimensional figure, and nets are the best way to calculate that. So if you look here, you have 2 pi r h as your equation plus 2 pi r squared. I apologize. This part represents the rectangle, and the second part, 2 pi r squared, represents the bases. So let's start with the bases. So you see how it says 2 pi r squared? That's because you have two bases now, and not just one being calculated for it. So once you calculate the area of one base, you can just multiply it by 2 to get the area of those two circles. And as I showed you here, this is the area for a circle, pi r squared. And then here you're going to calculate the area of the rectangle, which is a little bit trickier, but it's actually kind of simple when you think about it in terms of the volume of a cylinder. So it says 2 pi RH here. The reason that it says 2 pi RH here is because you're going to look at the height of the actual cylinder, which is H, and you're going to take that height of the cylinder, which is actually the height of this rectangle, and then you're going to take your equation 2 pi r, and you're going to multiply that by your height in order to get the area of the rectangle. And now you can use the approximations of pi, or you can use the actual value of pi and put it into terms of pi. So this is your equation of your cylinder as stated here. And if you look at the diagram and notice, each part of the equation represents the different shapes in the net, and that's also what I stated before. That's actually very important here because they're actually related terms. So 2 pi RH in forms of a rectangle is actually defining the body of a cylinder. So it's all relative in geometry. All these terms are very relative with each other, and surface area and volume, they're very they basically go hand in hand with each other, and that's also very important. So let's move on to cones now. Let's look at the volume of cones. And before we do that, let's look at the definition of a cone. A cone is a figure that tampers from a roughly circular base and decreases in size all the way up to a single point. So it's kind of like a cylinder, and that's important because cones and cylinders do actually have a very unique alikeness with each other. So as you can see here, it starts from a circle as it extends out in all sides, all infinite points of the circle to a singular point, or a tip or an edge, whatever you want to call it. But it's also called the apex of the cone. And basically, a cone is actually considered a third of any cylinder with the same exact measurements, and I'll get into that with this volume equation. So as you can see here, it's 1/3 pi r squared times h, and that's the volume equation for a cone. And let's actually go ahead and calculate that. So you see here, pi r squared, that's the area of your base. You're going to take 2 and you're going to square it because that's your radius, and that's 4. You're going to leave it in terms of 4 pi, and then you're going to multiply that by 1/3 to get 4/3 pi. And then after that, you're going to multiply it by your height. 4/3 times 8 is going to be 32 over 3. And then you're going to simplify it, and we can leave it in terms of 32 over 3, and you actually get 32 over 3 pi. So in geometry, oftentimes, you're not recommended to simplify your answer. So I left it in the form of 32 over 3. I'm going to leave it as that because you actually don't want to simplify it into a mixed fraction because that's simplified furthermost. But in geometry in general, you don't want to simplify your fractions because you might have to do other operations such as multiplication and division later on. But only for your final answer will you have to simplify. And if you look at the cone, I apologize. So if you look at the cone, it looks like a piece of the cylinder. And that's because it is. Because if you look at this equation, it's basically the same exact equation without this 1/3. It's pi r squared h, which is the same equation of a cylinder. However, this 1/3 is actually very significant. Because if you take the base of it, if you take the base of a cone, which is a circle, and you multiply it by a height, you're actually going to get an area of a cylinder. Because if you think about it, a cone is actually cut out. It's a cut out piece of a cylinder, because if you add these 3 of these cones together, you're going to get the volume of a cylinder with the same exact measurements, the same exact properties as this cone. So that's why you're multiplying it by 1/3. You're just taking 1/3 of that cylinder and defining it as a cone. So let's move on to surface area of cones. The surface area of a cone is pi rl plus pi r squared. The first part of the equation represents the lateral area of the cone. So what we've done here is we've just represented the net of the cone, and basically what we're showing here is pi rl. That represents the area of this netted body part of the cone. And of course you have pi r squared for that one circular base. And your lateral height will be, basically it's this extension right here. Your lateral height will be given on any circle, any cone. So the height is actually your axis in any right cone, but your lateral height is actually the sideways length that goes from the tip of any circle, the outer edge of any circle, all the way to the apex of the cone. So you're going to do pi RL, you're going to multiply those together, and then you're going to add it to your base pi r squared. And of course, these parts are included in the net of the cone. This is just a representation of the net of the cone. So let's move into our final subtopic, and that is oblique cones and Cavalieri's principle. So the volume formula of a cone only applies to right cones and not oblique cones. So that's all about oblique cones. Oblique cones are cones with an altitude that isn't the axis, which is basically opposite from other right cones. So oblique cones, say for example, in here, this is actually an oblique cone, and as you can see here, its axis is where the apex meets the center of the circle or of the base, the apex being the highest point on the cone. And as you can see here, this is a proper right cone, and that's the only way this volume equation will work for this cone. It will not work for oblique cones. You have to find your special cases. And also, let's mention the Cavalieri's principle. It's actually a very heightened concept, but then again, we are an enrichment platform here, so we're trying to get you acquainted to these enrichment concepts and these higher level concepts. So let's look at the Cavalieri's principle. It's actually a very high concept principle. And it's if two solids have equal heights and congruent cross sections at every plane parallel to the bases, they have the same volume. Now I'm just going to dumb that down to you. I'm down for you. Not that saying that you might need help understanding it if you don't, but it's actually very important because it should be looked at in simple terms, not complex terms. So if you take this cone and you slice it up, and then if you slice it up from every single possible plane, which is every single parallel upwards from the base, and you slice it up, you're going to get a circular cross-section that has to be equivalent to any other cone which has the same volume. Now, that's a bit trickier, but if you think about it, if you have a cone that has the same value as this cone, and if you have two separate cones that have the same exact volume, and they're both right cones, and you take a cross-section or a cutout from any part of this cone, it has to be with the same depth or the same proportional depth. It has to be of equivalent area. Now, I know that might still be confusing to you, but that's the simplest I can convey to you. And even if you chop this cone up and you reorganize every single one of its cross sections, it's still going to have the same area as its former cone. So that's it for today's video. Thank you for tuning into eCoreAcademy, our e-learning platform. Please like and subscribe on this video and hit that post notification bell to get notified on any of our latest posts. Please visit our website link at www.ecoreacademy.org to find any of our websites. Our worksheets, our notes that go along, and our integrated quizzes that go along with every single one of our videos, as well as visiting any of our socials at Facebook, Twitter, Instagram, Google Space, and our Gmail at ecoreacademy@gmail.com. So thank you guys for joining in. It's been AJ, and I'll see you guys in the next one. Peace.